Hello, bachon, and welcome. Today we are going to tackle a very important topic from our Unit 11, the dual nature of radiation and matter. We're going to understand the photoelectric effect, and I promise you, by the end of this, the concept will be crystal clear and totally safe for your exams.
Okay, so let's jump right in. But, not with some heavy formula or definition. No. Let's start with a simple puzzle from our everyday lives, something you might have even wondered about yourself. Just think about it for a second. You can sit in front of a really powerful, bright red heater for hours. You'll feel the heat, for sure, but you don't get a sunburn. But spend just a little bit of time in even weak sunlight, which has that invisible UV light, and you can get a really nasty burn. Why is that? I mean, common sense tells us that the brighter, hotter light should have more energy, right? Well, this is where our old understanding of light, the classical wave theory, just completely falls apart. That theory basically said that any color of light, if you just make it bright enough or shine it long enough, it should be able to knock an electron out of a metal. But the real experiments showed something totally different. It was the color, or what we call frequency, of the light that was the boss, not its brightness. This was a huge mystery, a real clash of ideas that needed a hero to come and solve it. And that hero, of course, was Albert Einstein. He came up with a truly revolutionary idea that didn't just solve this little sunburn puzzle, but it completely changed physics forever. Let's see what he said. Einstein basically said, hey, we need to think about light in a totally new way. It's not just one big, continuous spreading wave, no. Instead, he proposed that light actually travels as tiny, individual packets of energy. And he gave these little energy packets a name, photons. Now this is a fantastic way to picture it. Think of the photons of red light as energy weaklings. They're just not that strong. You can send millions and millions of them, but not a single one has enough punch to do the job. On the other hand, a UV photon, that's like an energy assassin. Even just one of them carries enough power to strike and cause damage. So you see, it's not about the size of the army, it's about the strength of each individual soldier. And this is the super simple formula that tells us the energy of one single photon. E equals h nu. Now, E is the energy, h is just a fixed number called Planck's constant, don't worry too much about it, and this nu is the frequency of the light. So here is the most important part, the crucial point. A photon's energy, its punching power, depends only on its frequency, which we see as its color. It has nothing to do with how bright the light is. All right, so now that we know what a photon is and where it gets its energy from, we can finally look at the beautiful and simple equation that Einstein gave us for this whole photoelectric effect. Now, pay close attention, because this is very, very important for your board exams. And here it is. The maximum kinetic energy of the electron that flies out is equal to the energy of the photon that hits it, that's our h nu, minus this thing called the work function, which we write as W. Now, just think of this work function as an exit fee. It's like a toll tax. Every metal has a specific exit fee that an electron must pay before it's allowed to leave. Okay, so we have the equation, but now let's actually visualize this whole process. How does this one-on-one interaction between a single photon and a single electron really work? It's actually a really simple three-step process. So step one photon comes in and hits one electron, giving it all of its energy, h nu. Step two, the electron immediately uses some of that energy to pay that exit fee, W, just to get free from the metal. And then step three, whatever energy is left over, that becomes the electron's kinetic energy. That's what makes it move and determines how fast it goes. That's it. This chart shows the story perfectly. Have a look. The dotted line there is the exit fee for the metal, the work function, which is 2 electron volts. Now the red photon comes along with only 1.8 eV of energy. Is that enough to pay the fee? No. So the electron is stuck. But then the UV photon comes in, packing 5 eV. It can easily pay the 2 eV fee, and the electron escapes with all the remaining energy. And look how simple the math is. The UV photon brings in 5 eV of energy. The exit fee is 2 eV. So what's the electron's kinetic energy? It's just 5 minus 2, which is 3 eV. See? It's just simple subtraction. No complicated calculations are needed to get the main idea. Okay, now for a very, very important section. I like to call these the silent killers in exams. These are 2 super common mistakes that so many students make, and they can lose you easy marks. Let's make sure you are not one of them. Okay, the first big mistake is getting confused between intensity, which is brightness, and energy. The wrong idea is that if you make the light brighter, the electrons will fly out faster with more kinetic energy. No, that's not right. The correct concept is that brighter light just means you have more photons coming in every second, so you'll get more electrons knocked out, but the speed of each individual electron stays exactly the same. Just remember this golden rule. Intensity controls the quantity of electrons, but frequency controls the quality, that is, the energy of each electron.
And the second big mistake is thinking that an electron can somehow save up energy over time. The wrong idea is that if you shine a weak red light for a really long time, it'll eventually charge up an electron enough for it to escape. This is completely wrong. The photoelectric effect is an instantaneous all-or-nothing deal. If one photon doesn't have enough energy, a million more just like it are not going to help. Just remember this. It's a single knockout punch, not 1,000 weak taps.
Chalo, let's quickly summarize everything we've learned to really lock it into our minds. And then I'll leave you with a little question that connects this topic to what's coming up next in our unit.
So, here are the 5 key takeaways for your exam. 1. Light is made of energy packets called photons with energy E equals h nu. 2. Electrons will only come out if the photon's energy is bigger than the metal's work function. 3. Einstein's equation, Ke max equals h nu minus W, is the master formula. 4. Remember, light intensity controls the number of electrons. And finally, 5. Light frequency controls the energy of each one of those electrons. If you get these 5 points, you are all set.
And that brings us to a final thought. We started this whole thing by saying our old wave theory of light failed, right? And we learned that to explain this effect, light has to act like a particle, a photon. So here's the big question. If something we always thought was a wave, like light, can also act like a particle, could the reverse be true? Could a particle, like an electron, also behave like a wave? Think about that. We'll explore the answer in our next explain.